So x minus 2 plus 2 cosine x, go ahead and hit enter. Let's go to our window. Now, here's what I want you to know about this. So we're finding the roots. Now, to be honest, there's probably another thing we're going to do more often than this if we wanted to know where this function equals 0. But let's just hit escape out of that. Let's do a zoom standard. So let's go to... So let's do a zoom standard window. There it is. Is that a zoom standard? Okay. And so we get that. And so we start to see this now. So if we want to know where this equals 0, it looks to me like there's 1, 2, 3 places where it crosses the x-axis. Do you think that there would be some back over here? Or over here, where it might come back? What makes you say that there would not?
The trend.
Well, the trend sure does, but remember, if you're only looking at a small piece of a graph, how do you really know?
Zoom out.
Well, you could zoom out, but I think if we investigate this, it would tell us. What happens as we go out this way? X is getting what? Bigger and bigger. Now, you tell me what's going to happen with this. What are the y's going to? Are the y's going to keep getting bigger and bigger? Because if this keeps getting bigger and bigger, and then I take away 2, and then what's 2 cosine do? Well, no, you are right, but I mean, just what's the cosine? What are the outputs of the cosine function in general? Between -1 and 1. Right? They're between, see how this domain and range stuff of these basic functions becomes important? Because I know that cosine is between -1 and 1. If I multiply that by 2, that means it's going to be between -2 and 2. And then subtracting 2. So I'm just going to be adding on like 1 or 2 or -1 or -2. But meanwhile, x is getting to be 100 or 1,000, right? And so isn't the y value just going to keep getting bigger and bigger and bigger? And if x is negative, it's just going to keep getting big negative, right? So if you just take a glance at the function and think, what's happening when x gets bigger this way, you say, oh yeah, there's no way. It's got to just keep getting up. So there's no way it's going to come back down to 0, right? So that's how you would know without having to zoom out and guess and whatever, okay? All right, so now all we need to do is trace, right? And so go ahead, Aaron, and hit trace. And let's go. It looks like there's one. Oops, there you go. It looks like there's one around 1, so type in a 1. Okay? Oh, there. So she just went right to it. So there you go, 1.10914. Now, if you're not seeing this many digits, because I think there might have been a few of you that were gone when we did our settings. Right now, if you go under, I think it's document. If you hit the doc button, go ahead and do that. And then settings. And document settings. And we want that to say float, not float 3 or float 6. Okay? So Aaron's is right. So if you escape out of that, and I think actually there's another place. If you go to menu, is there a settings under menu? Yeah, under menu there's also a settings. And then this, instead of float 3, if you're on the graph screen it says float 3, you want that to say just regular float. So under document settings, you want it to say float, and under the graph settings. Okay, so escape out of there. So that's one of them, 1.10914, and there's the other one. Now, here's what we'll normally do. So go to the home screen real quick. And go to the calculator portion. Okay, and now go to menu, algebra, solve, and since we've already stored it in f1 of x, well, let's just type it in. So type in x minus 2 plus 2 cosine x equals, go outside that parenthesis, but inside the other one, equals 0, comma x. And if we want to know where this function is equal to 0, most of the time we'll just do a solve right on the home screen instead of graphing it and tracing to the roots, right? The nice thing about graphing it is we know that there's 3. We could see it. Here, sometimes you'll get an error message. Go ahead and hit enter. You'll get an error message that says more solutions may exist. Like right here, if you put your cursor over top of that little thing, I think it might say something like, I'm not sure if we get an error message or can click on that, I'm not sure. But a lot of times that's what it means. More solutions may exist. Try specifying upper and lower bounds, blah, blah, blah. So when you do a solve, you're never quite sure. Hit OK. So you do have to be careful with that. But anyway, now look, what is this? Negative 1.1 times 10 to the negative 14th. It's strange that it did that, but actually that's 0. There's a root here at 0. Because, right, what's cosine of 0? Cosine of 0. 1. So put a 0 into our function. It'd be 0 minus 2, which is negative 2, plus 2 times 1. So I mean negative 2 plus 2, which is 0. So clearly there's a root at 0. Calculator just has some trouble sometimes, right? And so that actually means 0. And here's the one we had found, right, when we traced. And then if you hit your right arrow here a little bit, if you hit your right arrow, you better, I guess, up arrow. And then now hit your right arrow, and there's the other one, right? And so it found all 3 right there doing a solve. So we can do it on the graph screen, finding the roots, or we can do a solve. Okay. Aaron, go back to the graph screen. Let's delete that one out of there. And let's talk real quickly about number 29. 29 is do a fraction, so control divide. And then 1 over 1 plus x squared. And what they wanted us to do here, this is a little bit of foreshadowing. Go ahead and hit enter. This is what we're going to be doing in section 1.5. So tomorrow we'll be doing some of this. But what they wanted us to do is they want us to trace to the point 0, 1. Oh, is that right? Is that? Oh, shoot, that's not a very good point. I'll tell you what, I want to do a different one. I'm going to trace at 1. That's not a very interesting point. So go ahead and trace. But I just want to give you an idea of what number 25 and 29 were about. Okay, so what they want us to do is they want us to zoom in. They want us to give us a window centered at this point where the curve looks straight, right? In other words, like under a microscope. We want to zoom in. So what I want you to do is go to the zoom in. Go to window, menu, window, zoom. Zoom in. Okay? Let's put our center right about at that where that point was. Right about in there. Hit enter. Okay? And then do it again. Do it again. Do it again. Now, okay, stop right there. Now, go ahead and trace. Go ahead and trace. This will help you get it back to the center. So if you go to trace, type in our 1 again. Okay, go ahead and type a 1, hit enter. Did you hit enter? There, okay, it just takes.
It's under that.
Well, I see it is, but usually it'll center, do a little better job of center. Okay, go ahead and go back to zoom in. Let me see if we can type a 1 there when we're zooming in. I'm not sure we can. Oh, I know what we could then. Okay, so go down here about where that point is. Okay, and now hit it. That's a little better. Go back to trace. We don't do this very often, but sometimes if you want to get a point on the graph and get it to stay there. So is that our point 1? Type a 1 and hit enter. So that we're pretty close to the middle there. But the curve still doesn't look quite straight. I think it's taking its thinking here, doesn't it? And hit enter again. So you trace at a point and you hit enter, and then you hit enter again, and it'll actually stick it there. So now go back to zoom in. Go back to zoom in. Now you guys, on the ones you did on 25 and 29, weren't you getting pretty much horizontal lines, right? Now when they said a straight line, that doesn't mean horizontal, right? A straight line is, well, it seems silly to even say straight line, right? There is no such thing as a crooked line. If it's curved, it's a curve, right? In math, if it's a line, it's straight automatically. Go ahead and hit enter. So now you know right where that point is, and so now you can put your cursor right over top of it. It'll stay there. Hit enter again. Yeah, hit enter again. Pretty close. It almost looks straight now, right? Hit enter again. All right. So one of the things we're going to be talking about today, that's good enough. And then to answer the question, you can just go to your window and write your X min and max and write your Y min and max, and there's your window, right? Find a window centered at this point, right? And that's pretty close. All right. But here's the bigger idea. We're going to be talking about slope on a curve. Well, you can't do slope. We talked about that, right? You need 2 points. And so what we're talking about is a tangent line. Well, the idea is any curve, if we zoom in enough, if we look at a little teeny piece of any curve, we can make it look straight, right? We can make it look like a line. That's the idea. So this is how we could use our calculator to do that. So we'll be doing some of that in section 5. So that's kind of what I wanted to point out in this problem. Okay, thank you, Eric. And that's probably good enough for now. All right. So let's move to section 1.4 in our book, okay? So that is on page 36, essentially, okay? All right, so I want to get through this and give you some time here to work, hopefully. So one of the things I said, we were talking about the quiz, I said, things will start to focus in a little more. In other words, when we get to the next quiz, it's new stuff. And so it's not like you're trying to remember, okay, we did all this, we got to do this, or whatever. Now, obviously, all those things you talked about knowing what these functions are like, there may be a no calculator part to this quiz. And so, you got to know what the cosine graph looks like, or the sine graph, and those kind of things. So that part of it will always be there, okay? But the emphasis will be on these new things that we're learning. So it does help you to narrow in on what's going on. But as you're going through the days here, you can't study it all the night before. As you're going through the days, if there's stuff that we go over and you just don't feel right about, it's just not clicking, come in and see me, okay? Come in and see me. Very important. All right, here's what I want to talk about here in section 1.4. This is the beginning of calculus today, officially. Okay? All right. So we are going to be talking about a function f. I'm going to use the term right now. I'm going to call that the amount. So what do I mean by that? Well, I could have a function that represented distance, right? So that'll be the example we use. But it could represent a lot of different things. But we're going to do one for our example here that we're going to say it represents miles. So we could have a graph where this would be hours down here, and this would be miles up here. And if I had a point right there, if f of 2 equaled 100, what would you say that meant in context of this problem?
2 hours.
At 2 hours, you were 100 miles from someplace, from 0. Now, we don't know where we started, so we wouldn't really say you've traveled 100 miles, because I didn't really define it that specifically, right? So let's define it more specifically. As a matter of fact, in your book, they do. They talk about a car. Let's see. They talk about at afternoon on October 1st, 2000, a car enters Interstate, this is on 36, Highway 94 from the state capital on-ramp in Bismarck, North Dakota. For several hours, the car moves sometimes east, sometimes west at varying speeds. So at noon, okay, so that's our starting point. So the 2 in this case would mean what? 2 o'clock. At 2 o'clock, we were 100 miles which direction? It's a positive 100. So east is this way, west is this way, right? I mean, not really, I mean, that's north. But I mean, in our room, right? We're looking at a map right now. North's up here, south down here. East is here, west is here, right? So we're going east or west on the interstate, right? So positive numbers should be east. Negative numbers are going to be west. So this would mean, so with that definition now, if I gave you that, I would want you to say at 2 o'clock, the car was 100 miles east of Bismarck, right? Okay, so that is an amount. That's just the amount of miles we are away from a position, right? Okay, if the 2 was books and the Y value was dollars, maybe 2 books had a cost of $100 or something, right? I mean, so they could be varying units that we could use. So that's an amount. All right, this right here is going to be read F prime. That little symbol right here means the derivative. The derivative. Now, we've already talked a little bit now in the book. They don't know that we've already spent some time talking about instantaneous rate of change and stuff like that. So, to the authors of the book, this is the first you're hearing about some of this. Okay? So, when we write F prime, what we're talking about is the rate, and we're talking about instantaneous now. Remember we did the door opening, how fast is it opening at 1 second? The instantaneous rate of change of F. That's what we're talking about. So F prime is the rate function. So every function can be considered an amount. And then F prime is the rate of change of that amount. That's called the derivative. The derivative. Okay, F prime is the derivative. So on page 36 it says, let F be a function. The new function F prime called the derivative of F is defined to be the instantaneous rate of change of F at point X. So that would mean our graph of F prime, it's its own function now. And so it's got outputs. The inputs stay the same. It's still F prime of X, so the X is still ours. What would be the units over here? Miles per hour. It's always the Y units of F divided by the X units of F. I can't emphasize that enough. It's the Y units of F divided by the X units of F. That's going to be the Y units of F prime. The X units will always stay the same. It's the Y units divided by the X units. Remember we did slope, right? We talked about slope was involved. What do you do with slope? You take the Y's divided by the X's, right? We took the 2 points really close together. Remember when we did that? Okay, so let's say on this graph, we had a point at 2 that equaled 70. So we would write F prime of 2 equals 70. What's that tell you about this situation? At
2 hours.
Well, don't say 2 hours. I gave you more information than that.
At 2 o'clock.
At 2 o'clock, because I told you we're starting at noon. At 2 o'clock, you're traveling 70 miles an hour. The 70 is miles per hour now. You're traveling 70 miles per hour. Actually, we're missing one thing. Which direction?
East.
East. What would it be if we were traveling west? That would be a negative 70. Negative 70 would mean we were traveling west 70 miles per hour. So position can be negative. You usually think distance isn't negative. You're right. If you're talking distance traveled, it's positive. But we're talking position here. East is positive, west is, so think of an x-axis, right? So right now, you've got positive, which is on this side of 0, and you've got negative position, which is on that side of 0, kind of like a number line. And then when you're talking rate, you're talking about the direction you travel. So you've been in physics class, you know about this a little bit with velocity, right? It's got direction. It's kind of the same thing. So if we're traveling this way, so would it be possible for this value to be positive and this one to be negative? What would that mean if this y value was positive and this one was negative? Well, now we wouldn't know anything about slowing down. If this was a negative 70 and this was 100, what would that mean?
You're headed back west.
You're east of Bismarck 100 miles, So you're over here, but you're going back to the west at 70 miles per hour. Now, the slowing down thing is interesting. The slowing down thing, we wouldn't know anything about that. Well, all we would know is at 2, we would know where we were and how fast we were going. What would determine if we were slowing down or speeding up? That would be the rate of change of F prime, right? And so a minute ago I said that every function could be considered an amount, and its derivative would be the rate of change of that amount. So we could think of F prime as an amount. That's the amount of velocity you have at that instant. The rate of change of that would be the rate of change of your velocity. We call that F double prime. What would be the units on F double prime? Miles per hour per hour. What did I just say? When you do the derivative, you always take the y units divided by the x units. So if we do the derivative of F prime, the rate of change of F prime, it would be miles per hour, which is acceleration, right? And that's when you get into the speeding up and slowing down. Now you have to be careful. We're not going to get into this today, but you have to be careful. Just because acceleration is negative does not mean an object is slowing down. I don't want to get into the whole discussion right now. But just because some people like to use the term deceleration, I rarely will talk about deceleration because it gets confusing. Negative acceleration is not the same as deceleration. Okay? Think what's the most, from your science, what's the most famous negative acceleration? Gravity. Negative 9.8 meters per second squared, or negative 32 feet per second squared, right? It's negative because of its direction, not because speeding up or slowing down. If I throw a ball up into the air, what happens to it? Does it speed? When I throw a ball up into the air, does it speed up or slow down? It slows down. What's its acceleration? Negative 9.8. It's slowing down. But if I drop a ball, it's speeding up as it falls. What's its acceleration? Negative 9.8. It's still negative 9.8. Gravity is always negative 9.8 because of the direction it's acting. Okay? So negative acceleration does not mean speeding up or slowing down. It has to do with the velocity as well. Okay? When you throw a ball up, you've got the velocity acting in the opposite direction of the acceleration. That's why it slows down. If I drop a ball, I've got the acceleration acting this way and the velocity going this way. They're in the same direction. That's why it's speeding up. But anyway, we'll get into that more later on. So right now I want you to know about this notation. So you're going to have some problems on the homework. Guarantee you on the next test, you're going to have some problems where I give you a description of a function, what its units are, and I give you some of this function notation, and you have to write in words. I guess Caleb's had enough. You've got to write in words what it means, like we were just doing. Okay? All right, so that's a big thing we're going to do here. Now, so I jumped ahead a little bit here. This is in your book at the top of page 37, I believe, and it shows two functions. One is position, so this is the east of Bismarck position. So at 2, you can see it looks like it's right about 100, right? And here's the velocity, and at 2, it looks like it's right about 70, like we were just saying, right? And so, again, it's 100 miles east of Bismarck, and it's traveling east because it's a positive 70. But now let's look at a couple of things that are happening here. So as we travel, so in the car, I'm going, and what's happening at this point right here? Careful now. It's turning around. Right? Now, is it slowing down? I would agree. To change direction, it's got to slow down, right? I would agree with that. Now, but it's east, 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 traveling east of Bismarck. Right here, it turns around and what? It's coming back west. And right here, it gets back to Bismarck. Now, let's look at what's happening on the other graph. So let's look at this point right here when it turned around. That seems to be at 3. What's happening on this graph?
Stop.
This is the velocity, right? The rate of change. Didn't we just say to turn around it had to stop? So when it stops, its velocity should be 0, which is right there. When it's coming back towards Bismarck, which happens at 6, what's happening here at 6? Oh, wait. Once it gets to Bismarck, it keeps going west. So when's it turn around again? Between 6 and 7, what's happening over here between 6 and 7? It had to stop again. So forget this X right here. So when it was going west, what did you notice about the Y values over here? They're below the x-axis. The Y values over here are negative when this graph is going, well, when the car is going west, and when this graph is going down. Now, do you see the slope connection there? Remember how we said that the slope fits in here? Aren't the slopes of this have to be, now they're changing, right? But aren't these slopes positive here? Over here, the Y values are positive. Now the slopes become negative, the Y values are negative. The slopes go back to positive, the Y, do you see the connection here? So this is the derivative. This is, I guess, they call this function P. This they call V, but this would be the same as P prime. This is the derivative of P, right? The rate of change of P. And it has to do with slopes. Now, if we really investigate it, this almost looks linear here, right? So through here, it looks like the slopes stay about the same. Right here, what do you got? You got Y values that are staying about the same, looks like, right? Going down a little bit, but look about the same. Then all of a sudden, what happens right there? Gets a little steeper, right? The car would be speeding up a little bit. What happens to this graph? The Y values get a little bigger, right? Because the slopes are getting bigger. But then all of a sudden, somebody said it starts to slow down, right? So all of a sudden here, it starts to slow down, and that's what's happening here. The Y values start getting littler until it finally stops. And what would the slope be right there? What's the Y value over here? 0. Do you see then how the Y values here are the slopes of this graph over here? The slopes are changing. These Y values are changing. Now we get negative. Negative, I like to say negative and getting more negative. These slopes, right, they're like -1 slope, -2 slope, -3 slope, right? Over here, we're plotting that -1, -2. Well, it's actually those numbers, but you see what I mean? Now, it kind of bounces around here. We won't really worry about that right now because it's kind of curving, right? But it's going down this whole time. It's negative over here the whole time. So we're really going to be concerned with slope, going up, going down, positive and negative slope. And when we're graphing the slopes, we're thinking of the Y values. So above the x-axis, right, it'll be an important thing to be looking at. And below the x-axis is an important thing to look at because that's when these Y values are positive versus negative. But these Y values are the slopes of over here, right? Okay, so it seems a little confusing, a little jumbled, but trust me, we're going to be talking about this a lot over the course of the next 4 or 5 days. Okay, somebody asked me, when's our next quiz? When can I make up for this last one? When's my next chance? Right, it's going to be next Thursday. We don't have school on Friday. So our next quiz is next Thursday, okay? Unfortunately, we have parent-teacher conferences between then and the quiz, right? But I'll try to go easy on you. All right, now, oops. All right, turn in your book here to page, we can kind of skip around here. On 39, notice it has another definition of f prime, the derivative. It says the derivative f prime. Okay. All right. You haven't missed anything. All right. Okay, so So on at the top of page 39, it says the derivative defined as slope. So, okay, so we said derivative is the instantaneous rate of change of f. F prime is the slope of f. It's the same thing. Those two are the same thing. The slope at a point and instantaneous rate of change, same thing. Now, tangent lines. We talked about that a little bit when we were doing that thing at the beginning of the year with the door opening, right? Think of it, they talk about a car driving on a curvy road, and think of it as the headlights kind of thing. That's what you want to think of as your slope. So they've just drawn a few here. Here, if we want to do the slope on a curve, what we're really saying is what's the slope of this line. Now you can see tomorrow what we're going to talk about, that zooming thing we did a few minutes ago. See, if I zoom in right around this point, would there be hardly any difference between the black line and the blue line, or the blue curve? There'd be no difference, right, if you zoom in far enough. Now, again, keep in mind, the black line only shares one point with the blue curve. It only touches a curve at one point right around here. The rest of the time, the black and the blue have different y values, but man, they're not very different, right? If you zoom way in, the y values on this black line are pretty much the same as the y values on the blue line, okay? All right, so we got that. Now, back to this calculator document I sent you. So everybody pull that up. So if you've been messing around on your other stuff, you can go to document. Nah, don't do that. Go to the home screen. Go to the home screen. You can go to current, number 4. That's probably the easiest. And it should just pull up this document that I sent you. Okay? And you should get it here, Dave, as soon as you log in.
Get to it the other way.
How do you, what other way?
Like I hit current.
Nothing happened? So from the home screen, if you go to number 2, My Documents, and then now I've got a whole bunch of stuff you won't have. You should have that Calculus Period 2 folder, and it should be in there. Right arrow to open up that folder, and then it's called Derivative Grapher. Highlight that, hit Enter, it should open. Okay? Yeah, if you never opened it, if you never did open it, then, you know, because whenever you get a document, it gives you the option to open it or just escape out, whatever. Okay? So there it is. Okay, so here's what we have. This is kind of the same thing. The top graph is F. The bottom graph is F prime. So the slopes of this graph are the y values down on this graph. Okay? So if you go to the next page, so if you hit Control right arrow, and then you hit Control right arrow again, there we go. Now you've got a couple of choices here. You can either grab this white dot, or it's probably easier to just go over here and hit this little up and down arrows to move the point. Now yours might not move quite as smoothly as mine does. But what you should see, and the only reason we're not going to do anything with this, but I sent it just so if you want to play around with it, move that around, and just visually to get this idea in your head, the slope of the red graph here is getting plotted down here as a y value. So as you move to the right, what's happening to the slope value? It's getting less, isn't it?
Yes.
It's not as steep, but it's still positive. So what you have down on this graph is you have a positive y value that's getting less. And when you get to this peak, what's your slope? 0. Now that corresponds to the x-intercept down here. So you can see why we're interested in roots, right? The root on f prime actually is the peak on this graph, all right, which obviously would be something we might be interested in, right? You want the maximum profit? You're going to be interested in that point. Oh, well, it corresponds to when the derivative is 0, so that'll be something we'll use. Now the slopes turn what? Now the slopes turn negative and getting more negative. That's a weird thing to say. I hate to say the slopes are getting less because they are. They're negative. As you get bigger negatives, that's actually a littler number, isn't it? So that's something that's always a little confusing. So I like to say they're negative slopes and getting more negative. And so my y values are negative and going down, getting more negative. But then all of a sudden we hit what point where that switches? What's that called? The inflection point. When we hit the inflection point, all of a sudden they're negative but getting less negative. So down here my y values are coming back towards 0 And then right here, of course, we have a slope of 0 again. And then the slopes become positive again and start getting more positive, right? So the F graph, the F prime graph, the slopes of the F graph are plotted here. Okay? So that's a nice little document that you can play around with and just kind of get the feeling for what's going on there. Okay. So and it kind of corresponds to this picture that's in your book. All right. So next page. All right. Over to page 41. So on page 41, we've got a couple of equations that I want you to understand and be able to work with here. These sort of have to do with derivative, but they're along the lines of this position and velocity. It's the most common example we'll work with in calculus when it comes to derivatives. It's just the one that makes a lot of sense. But these rates do not have to be this. You could talk about profit, right? Dollars per book, right? The rate of change of your profit. So it doesn't have to be a time kind of thing, right? But in this case, this one's an easy one to understand. All right. So if we talked about if you throw a ball in the air. So an object in free fall, there's a couple of equations that we want to talk about. The first one they give you is h of t. H of t is the height of the ball at any given time. And this is, we're going to use the one in feet because your book examples are all in feet. So any object in free fall, if I throw a ball up into the air and it comes back down, it's going to be a parabolic kind of a graph for its height. It's going to go up but slow down, and then it's going to come back down and start speeding up. And you can picture that being that kind of a parabola kind of situation. Okay? It's h sub 0, which is the initial height, plus v sub 0 t. V sub 0 is the velocity that it's thrown with. So if I throw a ball in the air, if I just drop a ball, it has no initial velocity. That would be 0. Okay? And then minus 16t squared. So you can see there's a negative leading coefficient. You can see how it's an upside down parabola. So we want to just kind of commit that to memory. Okay? And you'll be working with it on a couple of your homework problems. Now, the derivative of that, or the velocity of that situation, so we could call it h prime, right? This would be h prime, or we'll call it v, either one. V for velocity. The nice thing about calling it h prime is we know it's connected to the h function, right? But it is velocity. It's the rate of change. All right, and this is in feet. Is v sub 0 the initial velocity you throw it with? So the velocity of the ball at any time is the initial velocity you throw it with minus 32t. Now, the reason for that is because of gravity, it changes 32 feet per second every second, right? So if you throw a ball at 100 feet per second, after 1 second, it's going to have lost 32 feet per second. After 2 seconds, it will have lost another 32 feet per second, right? Because of gravity, all right? So that's where that comes from, all right? So we want to be able to work with those two equations. Now, I'm not going to do any more with that. I'm going to let you do homework, but it's going to ask you some questions like this. It's going to say, okay, if I throw a ball from a height of 6 feet, so where would that go? Where would the 6 go? H sub 0. So if I throw a ball from a height of 6 feet, so you put a 6 there, with an initial velocity of 100, so that would go there and there. Right? So now you would have your H equation, you would have your V equation. How high is the ball after 4 seconds? So you put a 4 in for t, right? How fast is the ball moving after 4 seconds? Put a 4 in to that function for t. When is the velocity 0? Plug in a 0 on this side. You'd set this equation equal to 0 and solve it. When is it at a height of 200 feet? Put a 200 here and solve it. Now remember what we did earlier on the calculator screen where we did the solve? Where we just did the solve? So you could just take this equation, set it equal to 200, and then hit solve, right? So you're going to have a bunch of questions like that. So they'll give you information to plug into those, and then they'll just ask you these questions, and it'll just amount to plugging numbers in and or solving the equation to find it. Okay, that kind of stuff. All right. So hopefully you can do that, and we'll go over them tomorrow a little bit, but that's that section. Okay. The last thing I want to talk about, and so if you turn to page 42, and this is always probably the trickiest thing in here in the beginning. Now we'll see it on and on throughout the year, so it'll get easier to understand. But it's called the speed limit law, is what we call it. The speed limit law. I'm actually going to have you write this down, kind of word for word here, and then we'll break it into kind of more common language. Okay? All right. Let F be defined for all x in the closed interval AB. Okay? So it's nice, smooth curve. It's not undefined anywhere. No asymptotes, that kind of stuff. All right? Let M be any number okay, here we go. If f prime of x is less than or equal to m, and it would work for greater than as well. But if we usually talk about less than. If f prime of x is less than or equal to m for all x in AB, so that's just saying all the time, right? It's just saying that f prime is always less than or equal to m. Then f of b minus f of a is less than or equal to m times b minus a. So if that makes perfect sense to you, well, I don't even know what to say. Congratulations. Because I don't know why that would make any sense, right? But if we just very carefully break it down, we can make some sense of this, okay? So that's what I want to do. So f prime, what do we say f prime is? Instantaneous rate change, or the other word? Derivative, the other word? Slope. So you're right, f prime is derivative, but the two things, instantaneous rate change or slope. Okay? Let's talk about slope first. So this is saying that the slope is littler than m. So you can see why we're using m now, right? M is slope, right? Back in the algebra class. So our slope is always less than or equal to m. So think of m as the steepest the slope can be, right? The slope is always less than or equal to m. So m is like the steepest slope we could have on the graph, right? Okay, so m's like the steepest slope. All right, let's think of that. All right, let's look at a graph F. And here's a point A, and here's a point B. And so f of A would be right here, correct? That'd be f of A, the y value. And let's say f of B is up here. With me? So what would be a more common ordinary name for f of b minus f of a? That would be this y value minus this y value. In slope language. Rise. Wouldn't that be the rise? Wouldn't that be the rise? To go from here, this point, to this point, f of b minus f of a would be the rise. So I'm going to think of this side as the rise. Okay? And then what would b minus a be? The run. And then we said m is like the steepest slope, right? Oops. Steepest slope. Okay, so if we had a graph, so what this would be saying is, and this is less than or equal to, right? So this side would be like the most. So if the steepest the slope ever gets is 2, if the steepest the slope ever gets is 2, and we do a run of 5, then this would be the most rise we could have. So if we have a slope, the steepest the slope ever is 2, and we do a run of 5, what's the most we can go up? 10. That's what that's saying. And you're, duh, that's right. I mean, that doesn't seem like a big deal. Here's what it is. Here's why it's a big deal. Because what this says is if we know something about the slopes of the function, then we know something about the y values of the function. That's what it's saying. If we know something about the slopes of the function, the steepness of the function, then we know something about the y values. That's basically what it's saying. Okay, so the example would be if you've got a run, if the steepest the slope is 2, we're told that. If you run 5, the most you can go up is 10. That's what it's saying. Now, let's put it into speed limit language. Let's put it into car language. Okay, so instead of slope, let's call it velocity. Right? So let's call it velocity or rate of change. Velocity is less than or equal to m. So now m's not our steepest slope, but it's the fastest we go, right? So m is like our fastest speed, right? The fastest we go. So if we know we only go, this is our top speed, right? We're told that. Then what would this be? What would f of b? So if this is miles over here now, what would f of b minus f of a be? The distance we went, right? So this side, instead of rise, this would be the distance traveled, right? And then m here we know is our speed, our max speed, right? This is our max speed. And then what would b minus a be? This is hours, right? So b minus a would be the time that we were traveling. Okay, so if we know the fastest we went was 60 miles an hour, and we traveled for 2 hours, what do we know? The most we traveled was 120 miles. What this law is saying is if you know something about how fast you're going, you know something about how far you went. That's what the speed limit law is saying. So we can talk about slope language, we can talk about it in speed language. Okay, example. What would your homework look like for a problem that's speed limit law? So we'll use slope in this case. If it's given to you in car talk, then you can talk about it that way. But we're going to give it in function language. So if I tell you f of 0 is 3, and f prime of 2, or f prime of x is less than or equal to 4, for all x in blah, blah, blah. It'll have all that other stuff, but really what matters are those two things. Is it possible? Can f of 2 equal none? That would be a question you would get that would use the speed limit law. If f of 0 is 3, and f prime of 2 is less than or equal to 4, could f of 2 equal none? Yes or no? Well, here's what I would suggest. I would draw a picture. When I see f of 0 equals 3, what's that make you think of? A point 0.03. So what I would do is I would make myself an f graph, and I would graph the point 0.03. Then I would look at this and say, okay, what are they telling me there? Slope, great. Actually, that's perfect. When you read this, don't read f prime, read slope. The slope is less than or equal to 4. 4 is the most the slope can be, which means what on the graph? Every time you go over 1,
you can go at most 4.
The most you can go up is 4. Go over 1, most you can go up is 4. But you could go less than 4. Could you go down? Yes. Less than 4? Could it be negative? Sure. So if you go over 1, you might go down, you might go up, but if you go up, the most you can go up is 4. But they asked me, can f of 2 equal 9? Well, what's that mean? That means if you have an input of 2. So from here, if I go over 2, the most I can go up is 8, which would put me where? At 11. So could f of 2 equal 9?
Yes.
Yes. So and then it would say explain. Well, the picture, I think, is part of your explanation. You would say that you start at the point 0.03, and if the slope is less than or equal to 4, that means if you go over 2, you can go up 8, which would put you at 11. So f of 2 could equal 11 or less. I mean, if you really wanted to use function language, you could say f of 2 is less than or equal to 11. F of 2 could be anything below 11, but you could just say that in words. Okay? Could f of 2 be 19? Right? No. No. Right? So it has to do with rise over run. Right? Just rise over run. That's all it is. Okay, so they tell you a point, and they tell you the steepest the slope can be. That tells you about other points. And I think just a picture with rise over run is a great way to do it. So some of your questions will deal with the speed limit law, and that is the most common type of question you get with that. And that's how you attack it. Just plot it and think rise over run. Okay? All right. Your homework is the 1.4. So there's going to be a lot of stuff of looking at those graphs, a lot of the function language like we talked about at the beginning with speed and miles per hour and stuff like that. What does this mean? That kind of stuff. So go ahead and work the rest of the time. I'll put the answer book up here and come ask me if you got questions.